Okay, with that, I guess we'll get started with the speakers this morning. I'm Mike Zeke. I'll be moderating the session this morning. I'm from Lawrence Livermore National Laboratory. Our first speaker will be Devin Matthews. Devin has done his practicum at Argonne National Laboratory. Devin will be speaking with us about non-orthogonal spin adaptation of coupled methods with quadruple excitations.
Okay, so in case you didn't get it from the quite long title here, I'll be talking about chemistry today. So expect molecules and things like that. So first thing we want to ask ourselves is if we're going to do these calculations on molecules, we want to know, say, what is the energy of a molecule? What is the structure of a molecule? What is the electronic spectrum of a molecule? Anything we want to know about a molecule, we have to have a method, a computational way to get this information. And so what I'm going to be talking about today is called coupled cluster. So why would we want to do coupled cluster? Well, the first reason we want to do coupled cluster is that it treats electron correlation. That is, as the electrons are zipping around the molecule super fast, and they happen to bump into each other, there's this instantaneous repulsion between them, because they're both negatively charged particles. So you can imagine they're zipping around, this one bumps into this one, and says, no, you got to go somewhere else. Well, it turns out a lot of electronic structure methods don't actually accurately capture this physics. Instead, you might treat the motion of one of the electrons as an average field of the other electrons. And so you're missing this instantaneous dynamic correlation between the electrons. And that's what coupled cluster gives you. So the second reason you might want to is that coupled cluster is hierarchical. That is, you can start out with a somewhat accurate method. You can make it more expensive and get a more accurate method, make it more expensive, and so on. And eventually, you always reach the exact energy. And of course, the cost of getting this exact energy scales factorially with the system size. That's actually worse than exponential. So you can't really do that often, but it turns out that the quality of the result you get as you go up this chain improves quite rapidly. And as I'll show you, this method here in particular is essentially exact for most problems that you want to do. And the third reason we want to do coupled cluster is that it's mathematically appealing. It has a lot of mathematical properties and physical properties that are nice. It has size extensive, which is something that coupled cluster and other chemists talk about ad nauseum. It's orbital invariant, naturally truncated, and so on and so on. But we're not going to talk about those too much today. So let's say you want to do kinetics or thermodynamics. You want to do quite often. In order to get that often even qualitatively right, you have to have a very high accuracy in your calculations. And a lot of experience has shown is that you have, well, first of all, you have to do a lot of calculations. There's no one golden bullet that can get this right. You have to take things and you have to extrapolate them and add corrections and so on and so on. But eventually, if you get all the way up to CCSDTQ, the method I'm going to be talking about, that generally gives you 1 kilojoule per mole accuracy. You take everything into account. And that is generally enough to get complicated kinetics like this qualitatively and even quantitatively right. And so it's worth it to go that extra mile and go far and do accurate coupled cluster calculations. And let's say you have these complicated systems and you need to look at all the different structures of these systems. Maybe look at structures in vacuum, structures in solution, crystal structures, different crystal polymorphs that all lie very close in energy. Well, you need to have a very accurate method to differentiate between these structures. And again, coupled cluster, and especially going to higher orders of excitation like CCSDTQ, gives you the right answer and allows you to distinguish between these structures and determine which ones are the experimentally relevant ones, and then determine the experimental observables from those structures. Finally, when you have clusters or complexes, especially clusters and complexes which are somewhat weakly bound or dispersion bound like these, often the higher order effects, the things that you don't get until you go to the very expensive calculations, can actually inordinately large a part of your dispersion or binding energy. And so you can often get the wrong answer for a long time until you go to these very high coupled cluster orders, and then you can finally get the right qualitative and quantitative answer. So there's a lot of reasons that we want to actually do these very expensive methods. There's really no free lunch sometimes. And the final example is sometimes you have multi-reference systems. And multi-reference really is just a fancy word that means radical. So for example, we have something like parabenzine. We have an unpaired electron here, we have an unpaired electron here. But there's really two dominant, if you think, sort of Lewis structures or orbital configurations that describe this. This electron could be spin up, this one could be spin down, or they could be reversed, spin down, spin up. So our wave function is sort of a linear combination of these two different dominant descriptions. And if you think of your wave function as this sort of space, and we're going to make it two-dimensional because our brains don't work in 40 or 50 dimensions like the problem really is, we can put C1 here, C2 here, and if we do a somewhat accurate coupled cluster calculation, it essentially describes the wave function well in this area around C1. The problem is that C2 already is two excitations. This is singles and double excitations here, so it's already two excitations away. So it just barely gets described by our coupled cluster method. And all this stuff that we'd need for a really qualitative description is missing. But if we happen to go to higher orders of coupled cluster, we just keep adding on letters here, we can eventually start to describe both of our configurations in a somewhat equal way. Now, I'm not saying that doing really expensive calculations like CCSDTQ is the right way to do multi-reference coupled cluster. There are actually explicitly multi-reference coupled cluster methods in development. But when you do these calculations, you tend to not have to worry about these effects quite as much. You tend to get a lot more things for free. So that's another reason that they're mathematically appealing. So now that we know what we want to do coupled cluster calculations, how do we do these? What is coupled cluster? What are the actual computational things that we need to do? So in coupled cluster, we start out with a reference wave function. And this reference wave function is going to be essentially what you get from Chem 101. You draw out a bunch of horizontal lines that are your orbitals, your atomic or molecular orbitals, and you start filling them up from the bottom. You obey the Pauli exclusion principle and so on. And eventually you get one of these orbital configurations. And that is essentially our reference guess. We have a bunch of orbitals, and we put electrons in some of them. Then what coupled cluster is going to say is that now we want to write the exact wave function, the exact many electron wave function of our system, and it's going to include all of the different possible orbital configurations here. But what we're going to do is we're going to start with this one and then add this, pointer's not quite working, add this exponential operator here to it. And this T operator is going to take electrons and it's going to excite them from orbitals where we previously put them into different orbitals. And it's going to do that all the possible ways. And the exponential here is going to give us an exponential decay from this reference configuration. And so now we've included all the possible configurations. That means that if we choose the weights or the coefficients right, we get the exact answer. All we haven't done is said, OK, what are those weights? And to be exact, you have to include excitations up to the number of electrons you have. Of course, if you're going to search the possible space, you have to move all the electrons around. But you can cut this off at some point. So for example, if you cut that off at T1 and T2, that gives you CCSD, singles and doubles. If you add T3, that gives you singles, doubles, and triples, and so on. And now, once you've truncated this, your method is no longer exact, but it turns out to be very, very accurate, and it gets much more accurate very quickly the more letters, the more T's you add, although it gets more expensive as well. So what we can do is we can take our assumed wave function form, our ansatz, and we simply put that into the Schrodinger equation. And then we do a little bit of math. We project things on the left-hand side and so on and so on. And eventually we get these two equations. One of them on the left gives us the energy. And if we haven't truncated our T operator, if we include all the space, that's exact. And the equation on the right gives us a set of coupled nonlinear equations to solve that give us the amplitudes or the coefficients of each of these individual excitations. Those are the information we need to determine the wave function and to determine the energy. As I said, the problem is that they are coupled and they are nonlinear. And you're not even guaranteed a solution, actually, although in general you do get a solution. So now, what are the actual equations we need to solve? Well, this is the fun part. As chemists, we get to express our artistic ability and draw stick figures. And you end up drawing a bunch of diagrams like these. These are called coupled cluster diagrams, interestingly enough. And for example, if you want to do CCSDTQ, you end up with 183 of these. And then for each of those 183 diagrams, there's a set of rules that you follow for writing down the equation. and then you solve those equations. So I'm not going to talk about in too detail about what these are or how you look at them. I'm just going to show a couple simple examples. So one simple example is we have this diagram. We're going to take this thing on the bottom. The solid line is going to be a T, that T operator. And it's got 3 lines going in. Those are going to take electrons away. It's got 3 lines going out. Those are going to add the electrons back in somewhere else. So those are the 3 excitations. So that's a triples excitation. And then this thing on the top is just a piece of the Hamiltonian. And so we can look at that diagram. We can write down an equation. And everything's good. The problem is that the equation you write down here is what's called a spin orbital equation. That means each of those letters, each of those orbital labels is going to run over both spin up electrons, spin up orbitals, and spin down electrons and spin down orbitals. And not all possible combinations of spin up and spin down are allowed. There are spin selection rules. And so if you want to make your calculation actually feasible, actually efficient, you have to take advantage of those. And so for closed shell molecules, molecules that have all the electrons paired up, you can do what's called the orbital coupled cluster theory. But there you have to draw a lot more diagrams. And now it's not 183. Now it's somewhere in the vicinity of 700, 800. It's quite a lot. So you have to draw, for example, over here, you have to draw these 6 diagrams and get these 6 terms. And that's kind of gross, yuck. So can we do better? Turns out we can. Turns out there's a way to take this same diagram here, draw it again, and now we simply use different rules. And we can directly write down one equation now where we've put some extra notation on things. And this extra notation is going to tell us now we need to take, instead of just this one element here, we need to take a linear combination. So we build these linear combinations and put them together. And we get the same thing as on the previous slide. We get the same 6 terms. So there's 6 elements in this linear combination. We don't have to go through the trouble to directly write down all the diagrams, all the equations, and then put them back together. We simply get the final factorized form as it is. So that's what I call the non-orthogonal spin-adapted method. So now we need to put this in the computer, so we need to think, okay, how are we going to store all this data? Well, since these elements here, we had all those lines going in and out. And those lines essentially are going to tell us, going to count over the different orbitals. And so we can think of these things as tensors now. A tensor is basically a matrix where we tack on a bunch of extra dimensions. So for example, this F guy here is a piece of the Hamiltonian, and he has 2 dimensions. So he's really like a matrix. V now is another part of the Hamiltonian. He has 4 indices. So he's like a 4-dimensional matrix, 4-dimensional tensor. And then T1 and T2, again, have 2 and 4 indices. So they're 2 and 4-dimensional tensors. And all those guys, we can simply store just as matrices or as tensors. So you just simply put the data in, one element after another, and we don't worry about zeros or anything like that. We just put all the data in. Now for T3 and T4, we actually get a very special structure. We get symmetry among the orbitals. So if we move orbitals around a certain way, the answer stays the same. So we have to take advantage of this. For example, here, we store only I less than or equal to j, less than or equal to k. It gives us roughly a factor of 6 savings. So that's pretty significant. If you go to T4 now, it's roughly a factor of 24 savings. So that's critical. So in order to actually store these guys, now we have this sort of complex structure. What we're going to do is we're going to take the top indices, the ones that we're not putting any restrictions on. Now those look like just sort of a regular tensor. No rules for how to restrict the indices. So we store those as a tensor block. And then each block is simply labeled with what is the ijk value for that block. And we do the same thing for T4. And so then what we can do is we can take all of these full blocks here, and actually if you shut your eyes and do a little bit of voodoo, you can actually write those down as matrices, and then we call matrix multiply. And that's basically all a coupled cluster is a bunch of matrix multiplies. But then we have to loop over these ijks. In order to make things efficient, we have to worry about when are we going to reading and writing from disk, when are we going to be communicating between nodes when we parallelize. So what we can do is we can take our entire T3 or T4 quantity, that's all the ABCs and all the ijks, and we can chop it up. So we take a certain set of ijks, some of that will fit in memory, and we call that a hunk. And then of those, we can further chop it down based on spatial symmetry. You know, is the molecule have a plane of symmetry, things like that. And further chop it up and chop it up and chop it up. Eventually, we get down to the blocks. And this hierarchy of structure is going to allow you to stage data in and out from disk and to define what chunks of data that you pass between processors. And it tells you essentially what your algorithm is going to be. So the data structure really drives the algorithm here. In terms of actually doing the matrix multiplies, I told you you shut your eyes and sort of do some magic. Well, this is the magic you have to do. And it turns out you can't really do everything directly as a matrix multiply. There's only 18 specific combinations of tensor contractions you can do directly as a matrix multiply. And so this sort of restricts what you can do. So in the end, we say, OK, we wrote that down. We did the equation. Was it worth it? Turns out, yes. So if you look at the previous program that people would use for these calculations, that's MRCC. And you look at my new program, which is in C4. For CCSDTQ, you see roughly a factor of 5 to 6 speed up. And for CCSDT-Q, which is an approximate method, you see as much as 100 times speed up. So yes, all this trouble was really worth it. And so with that, I'd like to thank my group, especially Dr. Stanton, and all these people here on the right for their help. And thank you for listening.